All right, so on example 9, don't read up there, that it might give it away. On example 9, we're going to meet a new parent function. So before we get to this function, f of x equals that, we're going to meet its parent function, because f of x ends up being a transformation of a new parent function that I want y'all to get very closely knowledgeable about, or closely related to, okay? So let's come off here to the side, and we're going to look at a new parent function. New parent function. So you're going to add this to your mental catalog. Let's call him, we'll call him j of x. How about that? J of x equals, and it's one of two versions. He has two different forms, and they're identical to each other in their physical features. Their graph is the same. They have a different genotype, if you will, but different or same phenotype. So it's the absolute value of x over x, or you could flip that, x over the absolute value of x. So, is this your slide? No? It is. Is this a rational function? Remember, a rational function is a ratio of two polynomials. No, it's not a polynomial. Absolute value of x is not a polynomial, but it is a ratio. It's a ratio of two functions. So notice that it almost looks like it's equal to 1, yes? X over x would be equal to 1, but that's not the case because we have the absolute values up there. So the absolute values could be either in the top or the bottom as long as it's only in one place, and we have a ratio. What would be the domain of J? It is a good question. Are we at risk of taking square roots of negatives? No, we don't have any radicals. Are we at risk of dividing by 0? Do we have any denominators? Yes, we have a denominator. It's either x or the absolute value of x. There's one value that's not in the domain. Don't overthink it. What is it? 0. X can't be 0. X cannot be 0. So it's the set of all x such that x can't be 0. I didn't even show the analysis, but remember we would take the denominator, all of it, and say it can't equal 0 and solve. You're pretty much done. All right, now, based upon what we've learned so far, is that a discontinuity? 0. Does the graph live to the left of 0 and to the right of 0? Yeah, if it doesn't live at 0, that's the only place, then it lives to the left and right. It is a discontinuity. It interrupts the flow of j of x. When you plug in, what do you get when you plug in a 0? Like j of 0, what do you get? You get 0 in the denominator, and what's the absolute value of 0? 0. You get 0 over 0, right? So based upon our experience, you would think that that graph has a what there? You would think it has a hole there, okay? Well, in this case, you would be incorrect. 99 times out of 99.5 times, a lot, 0 over 0 means hole. And every time for a rational function. So if you have a polynomial over a polynomial, 0 over 0 means hole. This is not a rational function. It has an absolute value. So it's the exception to the whole rule. But it's pretty easy to spot the exception because it has what? Absolute values. Everyone sees the absolute values? They're easy to spot, right? Yeah, good. So it's not a rational function. So what's going on there? Well, I'll show you. We are going to decompose this gross into what's called a piecewise function. So put an open brace, make it large, okay? So a piecewise function. Hopefully you've seen them before, but if not, I'm going to teach you. A piecewise function is exactly what the name implies. It's a function that is made up of pieces, and it is very, very wise, okay? It has different functions that define it on different non-overlapping intervals. If we had overlapping x intervals, it wouldn't be a function. It would fail the vertical line test. So think about the mythical creature, the centaur, right? You might know what a centaur looks like. If you've seen that creepy Old Spice commercial, then you really know what a centaur in the shower looks like. What's the centaur? Yeah, part horse, part man, okay? So he's like a piecewise function. Where does it change from horse to man or man to horse? Not quite the legs. The waistline, right? The waistline. So below the waist, it's a horse. Above the waist, it's a man. That's pretty much what a piecewise function is. It's the centaur of the mathematical world. It's part one graph for some values of x, part another graph for other values of x. But it could be as many parts or pieces as we want. We are going to now decompose this, which is essentially, we're going to be writing kind of like a primitive computer program. So if you've done any computer programming, this is going to feel like that. We're going to explain to someone, like a machine, a computer, how to take the absolute value of a number, okay? So let's go ahead and look at if the thing inside the absolute values, which we're calling x, if it's already a positive number, like 5, how would you tell someone to take the absolute value of a positive number like 5? What would you tell them? Keep it the same, right? Keep it the same. So just take whatever's inside the absolute value. So that's going to be just x, and we're decomposing this one. All over the denominator is just x. Now leave a little space there. We're going to put a comma. This is now where we define where that happens. So we get positive values of x on the number line to the right of what number? 0. So we put x is greater than 0. So this is like a computer program in the sense that it's like an if-then statement, if you know what those are. We're basically saying if x is greater than 0, if x is a positive number, then in the numerator, the absolute value of x is just that x value. That's all it is. The next command would be else, right? Which means otherwise, if x is less than 0, which means negative, how would you tell someone to make a negative number positive? Yeah, some people say just take away the sign, like physically break it off, throw it away. But, you know, computers can't do that. So we can instead multiply it by -1, or take the opposite of it. All right, so if x is less than 0, the absolute value of x is going to be the opposite of x, or -1 times x. I wrote that in the numerator. All over, of course, the denominator is just x. Now let's try it out. Pick a number less than 0. -2. So when I'm looking at the piecewise function, x equals -2, which piece am I using? The bottom piece, because it's less than 0. So when I plug a -2 in for x, I get negative times -2, which is +2. It works, right? So I've defined the function to the right of 0. I've defined the function to the left of 0. What about at 0? Should I put like greater than or equal to here, or should I define it at 0? No, why not? X can't equal 0. It's not in the domain. Got it? So that's why we find the domain first. Now let's simplify. After we found the domain, let's simplify. What is x divided by x? It's 1, right? 5 divided by 5, 10 divided by 10 is 1. What is negative x divided by x? -1. There you go. So we have just decomposed this ratio of two functions into a piecewise function. It's essentially the horizontal line y equals 1 to the right of 0, and the horizontal line y equals -1 to the left of 0. And it's undefined at 0. Let us go ahead and sketch the graph of j of x. Y-axis, x-axis. All right, so here's how you're going to want to do it. Come up here and label that as 1, and maybe label it to the left. Symmetrically go down about the same distance and call that -1 and label it on the right. Okay, so the top piece says when x is bigger than 0, draw it as a 1. Well, we can't draw it at 0, so we're going to put an open circle, and then I'm drawing a horizontal line to the right. And similarly, to the left of 0, it's -1, so we'll put an open circle around -1, and we'll draw it going out to the left. So there is what the graph of j of x looks like. And you're going to want to memorize that. Okay? It's just two horizontal lines that are broken at x equals 0. Is the function defined at x equals 0? No, right? I put an open circle top and bottom. It passes the vertical line test, right? Because there's no sharing violation. That is a discontinuity. Is it a hole? Would we call that a hole? Not in the sense we defined a hole. We do have two open circles, but not every open circle we call a hole. Remember, a hole is a vocabulary word, not just a descriptive word. A hole is a removable point discontinuity. That's a hole. The graph has to be connected on both sides of the hole. Someone came and swiped it out. That is the only thing we call a hole. Otherwise, we can call them open circles. So what we have there is not a hole. Is it a vertical asymptote? No, because a vertical asymptote is an infinite discontinuity. And do these y values go up to infinity or down to -infinity? No, they never get to x equals 0 But as they do, they're getting closer and closer to 1 and negative 1, not infinity or negative infinity. So it's not a VA. It's not a VA. Okay, but it is a discontinuity. Now, question. Do you think this is a non-removable or a removable discontinuity? Non-removable. Good. Because remember, the criteria is, if I gave you a little manhole cover, there it is, could you move that up and, ooh, I took too much. Took too much. That's me. That's me at a buffet. All right. Can I move this point up or down and make this graph continuous by putting it down at one place? Can I make it continuous? No. If I put it up here, I plugged one of the holes, but it's not continuous. Put it in the middle, it's not continuous. Put it here, it's not continuous. So there's no way to redefine it to make it continuous. So as y'all said, it is non-removable, like the vertical asymptotes. It's non-removable. Okay. Now, I already heard someone, maybe they read it, maybe have experience with it. As you're coming in here, approaching negative 1, you physically have to do what at 0 to get up to the next value? Jump. Okay? So this is called a non-removable jump discontinuity. A non-removable jump discontinuity. And these do not appear in rational functions. Polynomial over polynomial. That's just going to be holes or VAs. These typically come from piecewise functions. And of course, our function was really a piecewise function in disguise. Okay? So it's one of the few types of functions that you can express as a single equation, but yet it can decompose into two different ones. And it's because we have what symbol there? What is that symbol? The absolute values, okay, which could be in the top or bottom. Okay, so this is a new parent function. You want to memorize what the graph looks like and what it's doing. I use J of X because, no disrespect to Michael Jordan, but I call this graph the Jumpman Graph, okay? I think Michael Jordan is Jumpman one word. This is jump space man, Jumpman. All right, so Jumpman is a new parent function. It is the singular exception to the rule that says when you plug in and get 0 over 0, you get a hole. In this case, when you identify Jumpman or its parent or its transformation, 0 over 0 doesn't mean hole. It means what? Jump. Right. Now, depending on where you go in the world, it may not be called Jumpman. He made an appearance on Dora the Explorer one time, and they referred to him in that episode as Señor Salta. So if you want to refer to him as Señor Salta, it's bueno. It's okay. Apparently, in Colombia, he's known not by Señor Salta, but Hombre Trepador. So anyway, those are all his names translated. You don't need to know the name. You just need to know what the graph looks like and identify it from the equation, okay? Jumpman. 0 over 0 here is not a hole. It's a what? Jump. It's a jump. Because it is a what type of function in disguise? What do we call those? Piecewise. Yeah, now incidentally, we use the open brace to categorize the pieces. We don't put a closed brace at the end. It's just an open brace, okay? That's just how the format is. All right. So now let's look at f of x. F of x is a transformation of Jumpman, okay? How can you tell he's a transformation of Jumpman? Well, it's a ratio, and what do you see? Absolute values, right? We have absolute values of a linear function, that's an x to the first, over a linear function. What is the value that is not in the domain here? What's the domain of f? X cannot equal who? 3, that's the only one, okay? If you plugged in a 3 to the top and bottom, we know we get a 0 in the bottom. What do you get when you plug a 3 into the top? 0, right? 0 over 0 in this case, is it a hole? No. We can immediately say that f, or f of x, has a jump. You can refer to it as just a jump. And we say at x equals 3. We don't list it as an ordered pair. Just like the other non-removable, the VA, we say at x equals. Now I'm going to show you why this works. And in doing this, we're going to review transformations of parent functions, which are going to come up again here shortly. In Algebra 2, hopefully you investigated transformations of parent functions quite a bit. But here it is. This is called standard transformation form. Standard transformation form. So we'll go through this very quickly today, and then we'll look at it a little bit more in detail later on. All right, so here's what it looks like. Y equals, you have an A times f of b times x minus c, close, and then plus d. Okay? So what this is you have some parent function or original function f of x. And if you know what the graph looks like, you can envision it in your head. But multiplying by a or b or adding or subtracting c and d in this fashion to any equation of any function will manifest itself in the exact same way on the graph of those functions. They all affect the graph in the exact same way. So there's really two things that are going on here. The first thing I want you to focus on is we have an outside and an inside. A and D are outside the function, right? It's f of blob. The A is in the front, the D is in the back. If it's affecting the graph on the outside, or the equation on the outside, it's affecting the function values, or the y values. So that's going to affect the graph vertically. If it's on the inside, and we have two variables on the inside, f of, that's going to affect the graph horizontally. Those are affecting the x values, the inputs. All right, so that's the first dynamic that's going on. The other thing that you need to understand is A and B are multiplied or divided, whereas C and D are added or subtracted. That's the other dynamic. Anything that's multiplied is going to be a dilation. It's going to be a stretch or a compression. Anything that's added or subtracted is just going to be a shift or a translation. Okay? So if you combine those two, you can read it from left to right. A is going to be a vertical stretch or compression by a factor of A. If A is negative, like negative x squared, it's also going to reflect it across the x-axis. B then, multiplied on the inside, is a horizontal stretch or compression, like Wurstfest, playing the accordion. Okay, stretch it or compress it horizontally. If B happens to be negative, your x values are going to switch across the y-axis. Inside, if C is added or subtracted, it's a horizontal shift, left or right. And outside, if D is added, it's a vertical shift, up or down. So again, that's a review. We'll cover it in more detail later on. But here's a good chance to review it right now for our new parent function. I'm going to rewrite f of x in standard transformation form. Okay? So let's do that. F of x equals, in the numerator, inside the absolute values, I can factor out the 5. And that leaves me 5 times x minus 3, all over x minus 3. So there's my first step. All right, now there's a property of absolute values that says the absolute value of AB is equal to the absolute value of A times the absolute value of B. So why is that important? Well, that means I could bring my 5 on the outside and put it in front, times the absolute value of x minus 3, all over x minus 3. That is writing it in standard transformation form. The 5 in the front is an A value, and the minus 3 that occurs twice is a C value. Okay? It's a C value. It's being added or subtracted. So what would the 5 do if you multiply it in front of any equation to the graph of that function? Stretches it how? Vertically, right? So like 5x squared, the parabola is going to be narrower. It's going to stretch it vertically. That's going to be a vertical stretch by a factor of 5. Let's see what that does to our graph. If our parent function goes from -1 to 1, and you stretch it vertically by a factor of 5, now it's going to go from where to where? Multiply 1 and -1 by 5, right? It's going to go from -5 to 5. So let's come over here and sketch that. Here's -5. Here's +5. What else? We're going to move it what? X minus 3 moves it. It's inside, so it's actually going to be left 3. Yeah, it shifts it left 3. So there's what the graph looks like. And now you can clearly see that at x equals 3, the value that gives us 0 over 0 is not a whole, but a vertical asymptote. All right, and we'll stop right there. Coronado, you can go. Everyone else can go. So memorize Jumpman. It's a new discontinuity, non-removable